Today we're going to have a look at the 4NEC antenna simulator again. This is the final tutorial. We've done in tutorial 1 the user interface. In tutorial 2 we've outlined the editors and how to enter in your information for your own antenna. And in this tutorial number 3 we're going to look at some of the more esoteric tools, the optimiser and the matching. So let's have a look and see what we have here. We'll start off with this antenna which I've pre-configured. This is what it looks like here. It's a dipole, and behind it it has a reflector. Now the pattern, as you can see, is pretty well a dipole type pattern. There's a small amount of gain, but not much. And so this reflector is not particularly optimized or set up for a gain type of situation. So we're going to use the optimizer and the evolver to see if we can let 4NEC do the hard work for us. Okay, now I'll just go through and show you how the actual antenna is defined. When you use the optimizer, you need to have symbols. Now, symbols are very simple. For example, if you had a spacing between the two elements of 2 meters, you could just have 2 in there, because you can notice here that it says scaling equals meters. So you could just have 2. But of course the optimizer won't be able to do much with that because it's a fixed number. So what you need to do is you need to give that a name. So we'll call that spacing. Now if you give it a name, you also need to tell it what the value is, the initial value. So you go to this name is called a symbol. So now we go to the symbols and put spacing equals 2. The spacing between the radiator and reflector. This is just comment fields here. And to enter in symbols, you just simply put whatever you want to call it. It could be, I don't know, height 1. And then you just put an equal sign and then say 5. And if you want to, you can just move the cursor over there and just put test or something, whatever you wish. So anyway, to delete that, you just press the delete key on your keyboard once it's highlighted. And we'll just save that. Okay, so there you go. So I've set up these symbols here. So I've said the height is 3 meters, the spacing is 2 meters, the radiator length, rad length, is 3, and the reflector length is 4. Now these aren't particularly optimized for SWR or anything else, but we've done that, or I've done that purposely so that we can let the program optimize. So I'll just explain here what I've done, and this may help you to get over some of the hurdles. When you're naming things and setting up symbols, what I've done here is, if you have a look, the antenna is centered on this origin point here on the Z. So I've centered it over Z. Now this element, reflector element, is here on a value of Y. It's a positive value of Y. Now if you were to go this way here, that would be a negative value of Y, in the same way that this is plus X, and if you were to go over here, that would be minus X. There's no point in going minus Z because then you'd be underground. But so you can see that Z will always be positive. Now I've centered the antenna here at the origin of the junction of these 3 axes. So the antenna elements will be going plus X in this way and minus X in this way. So that's the reason why, if you have a look here at X, I've actually said, okay, the radiator length is minus radiator length divided by 2. You notice you can actually put in mathematical operators, and the little, you notice there is the divide symbol. So what I've said is the radiator length is 3, but in the geometry field I've said one point, this point here, is actually at minus radiator length divided by 2. So in other words, minus 3 divided by 2, or minus 1.5. So this point here is minus 1.5 on the x-axis. If you have a look at the other end, which would be this end here, it's radiator length divided by 2, but notice that's an implied plus. So radiator length is 3 from the symbols there, and so 3 divided by 2 is plus 1.5. So that will be that point there. The same thinking has been used with the reflector length. So that's why it has a minus sign in front of it at this end. So I just thought that would perhaps help you a little bit in defining your own antennas. Okay, so we have our symbols, we have our height, our spacing, radiator length, the reflector length. The frequency I've set to 50 megahertz. The ground type is a real ground. The main, it's rocky steep hills, which is where I live, and that should get us going. Okay, now I'll just save that to make sure that's okay. Now I'll close this, because when we use the optimizer we have to close the editor. Okay, now the optimizer is here on the main screen, and you simply go to the calculate menu option and go to start optimizer. Now the optimizer has a number of different operations or functions. You can evolve, and what this will do is, this is a way of actually doing a bulk evolution. It uses genetic algorithms, which I won't bore you with the details, but basically it just keeps trying things to see if it can reach a point where you get an optimized or an optimal solution to a particular problem. So for example, you may wish to say, okay, I want the minimum SWR, what will the radiator length be for that? So you can let it evolve, and you can set the limits between, you can set, okay, I want the radiator to be between such a value, let's say 1.5 and 3, so, and then you can restrict it in that way, and it will just keep on moving about using a genetic algorithm until it finds what is a reasonable solution. The optimize function actually is more detailed and will actually do things on a finer level. The sweep gives you it sweeps the frequency, or it sweeps the values, and it will show you what the effect is over that range of values on SWR or whatever you wish. The convergence test, this conv test, is really more something which is done by, for NEC2, it changes the number of segments and a few other factors if necessary, and it basically says, okay, if I change all these things, will the gain and the other parameters which I produce as a program converge to a point? Now the point of that is basically, is the antenna a stable design? So that's the reason. You probably won't use that very often. I don't use it, but anyway, it's there if you do need it. So basically it's to test the fragility or stability of your antenna design. Okay, now you'll notice the variables here are automatically popped in. Now these are the variables that the optimizer has available to work with. You can select which ones or which combination of variables you wish to work with. So, and also, if you notice here, you have SWR gain, front to back, front to rear, the impedance, the real component, the reactive component, efficiency, and so forth. Now, you can choose how much effect you want each one of these factors to have in the optimizer. So let's start with, for example, evolve. Now, let's say that we want to have the most front to back, and we want the reflector length to be the only factor that we're looking at. So, and we say, okay, we want the reflector length to be between 2 and 8. Well, it seems a little bit high to me, so let's make it between 2 and 5. And then, so we've given the front to back ratio a factor of 100%. So that is the most important factor in our evolving simulation. Then you just press start. Oh, sorry. These things here are just various ways that the genetic algorithm will work. So you can play around with those. There are various types of different systems in use here. I just go for the default at the moment. Okay, just press start, and what you'll see is that there are a number of screens which are moving along, giving you information on how it's going. Now remember, we're looking for maximum front to back. So the program is trying various things. You can see the results of that here. Saves you sort of going back and forth in the editor and doing it. As you can see, it's a very, very useful program. It has a huge number of applications, and it's quite accurate as well. So now it seems to be sort of bouncing through between things that are effective and not, but it's keeping note of what works and what doesn't. And this is the evolve function. The evolve function, you just let it run, and at the end of it you will have a solution. You can see that it's starting to converge now on a solution. Now, because of the restricted time we have here, I'll stop that and just leave it there for the moment. And you can see that it has settled on a reflector length of 2.991. It's got a front to back of 12 dBs. Not too bad. We'll just have a look at the horizontal display. Yeah, well, there you go. So it's gone from basically a dipole to a Yagi to a two-element Yagi type display. If we have a look at the JIG, we have a front to back here of in the vertical plane of 11.5 dB. The beam width is 35 degrees, and the gain is 9.85 dB in that particular configuration. And here you can see the beam width in the horizontal plane is 90 degrees and 9.65 dB gain. Okay, so that's the evolve function. If you want to, you can update this in the NEC file. If you press this, you can, and it says which generation do you want to save, so you can choose which one of these you wish it to save. If I pressed OK, it would update the file and actually change the reflector length from 4 to 2.9 in the editor file. But I'm going to cancel that because I don't want to do that at the moment, because I'd like to go and let the optimizer, we're going to go through and try each particular function here. Now I'll just do the same thing this time with the, actually I'll do the radiator length. If we have a look here, oh wait a minute, sorry, I'll just run the program and we'll have a look at the SWR. It's 1.93, so I will start the optimizer, and this time I'm going to use the radiator length, which is set at 3, and we have an SWR of 1.93. Now I'm going to use not the evolve but the optimize. So, and I've just selected radiator length. Now you can select, for example, reflector length as well, and you could say I want you to try various values of both of these until you get the appropriate value. But I'm going to, and just click on that to bring it out, to take it out. But we're just going to use the radiator length. Okay, I don't care about it front to back, so I'm just going to use SWR as my only criterion. And remember, we're using optimize, and then we press start. Now we have a look here. Here's the SWR, and you can see it's trying a few different things, and it's varying here the length of the radiator. It says, okay, I got it down to 1.5 in at 2.9211. Okay, we can just say resume. See if we can get it any lower. No, that's about it. So it got it down to 1.539. Now I will update the NEC file with this one, and I will say save. Okay, now if I was to run this again, calculate, you'll find it's now 1.54. And if I was to open up here, we have a look and we notice the radiator length has been changed to 2.918779. Okay, now let's have a look at using the optimizer, or we'll use the optimizer, and we'll say, okay, we want the reflector length and we want to have the best front to back. So we're using the optimizer, not the evolver this time. Okay. You notice that these values here are changing, the reflector length is changing, and it's now evolving down, and you notice the pattern is becoming very much more like a Yagi. Okay, so it has a front to back of 12.26, a gain of 9.9 dB. The SWR is 2, so you notice it has affected the SWR, which is quite normal. Now I'm going to update the NEC file with that as well. And so there we go. Now we could, for example, say, okay, we'll have the optimizer and we'll put the front to back in, but we'll also take account of the SWR. So we want them both. And so we're going to change the reflector length and the radiator length. So we're going to use both of them. So we want front to back and SWR as factors in the decision. And you can see it's trying various combinations to try and get them both at the best. So at that particular value, or reflector length of that, radiator length of that, it says, okay, the best I could do is get an SWR of 2 and a front to back of 12.25. So we'll say, okay. So what we'll do is we'll put that, and we'll take the spacing into effect as well. And then we'll say, okay, let's try again. Now this time it's actually got 3 figures to work on. So the length of the reflector, the length of the radiator, and the spacing between the two. See that the front to back is it's staying pretty constant, and we managed to get a gain of 9.9 dB and 1.9 as a SWR. So we'll leave it at that, and we'll say okay. Now let's look at something else. So that's the optimizer. Now we'll look at something else. We say, okay, we've still got a bit of SWR, 1.97. So we go to the, well, I should have told you a bit more. Okay, so you go to calculate LPI T matching. Now this gives you various networks here. So which one would you like? Well, let's go for this L network here. So I'll say I'll go for the low pass L network. So if you want to match a 50 ohm load to the impedance, which is 98.5, it's imported that from here, and at 50 megahertz, then this is what you need. So you'll need to have XS, which is this series component of 157 nanohenries and 32.7 picofarads for the parallel component here. And that's all you do. And you can choose any one you want. If you want a pi network, there you go. Gives you all the values you need. Now let's say, and as an example, if you press use network, it will actually say, okay, well, I'll calculate it and tell you what your SWR is going to be. And if you have a look here, SWR is now 1. So using this pi network, you'll get 1. It's managed to match it. So there you go. It's figured out all the components for you. And the same thing can happen for these other ones here. Now let's say that you're a stub match person. You want to use a stub. All you do is, when you're in this one here, you just go to stub match, and you say, what sort of stub? Do you want a series section, a parallel stub, or a series stub? So we'll go for parallel stub, and we'll say, okay, we have an impedance of 50 ohms, we have a load of 98 with a 2.73 reactive component. That's the J part. Okay, so if you want to use, what do you want to use for the line? That is the antenna to the stub. In other words, the antenna there to the actual stub section. If we're saying 50 ohms, a velocity factor of 0.66, but you can try different other types of lines, as you can see there. You can see you can choose any one of those. What do you want to use for the stub? Well, in this case, the default is 75 ohms with a velocity factor of 0.66. And again, you can try different things. Some things won't work. They simply won't be possible, but it'll tell you if it isn't. Okay, now if you want to use, there are normally multiple solutions with stubs. Some of them may be physically better able to be implemented than others. And that's why you have the A and the B options. You see this one's quite short and this one's a bit longer. So you've got your choice. Now select solution, open stub, short stub. Well, let's go for short stub. And there you are. Those are your two solutions. Now if you want to see what your SWR would be if you use that stub, just go use stub and do the frequency and it would say 1.01. So there you go. If you say want to use a series section, and this will again describe everything here. Line length L2. This is L2, which is the matching line. 75 ohms. Now, let's say we want to use, I don't know. Let's see what's interesting. Some twin flat line 300 ohms. Okay. So we can see we have here the solutions. Or if you want this particular solution here a little bit longer, it's a bit short, isn't it? So if you want that a bit longer, there you go. And if you press use solution, 1.02, there you go. So very, very easy. Okay. Well, that's the matching and optimizing and the stubs. I think that would probably be enough to get most people started. I hope you have a lot of fun with this antenna. Oh, by the way, this here, it shows you the stub in place. So you can see here. Oh, something I haven't shown you, the 3D. If you go to this button here, 3D, it will show you the 3D display. Now, at the moment, that's the antenna, so you can see there. And if you actually go here, and it says hide pattern, we want to actually look at the pattern. So you go to multicolor, and if you want, you can zoom that and make it bigger. We'll just make it a little bit smaller so we can see it a bit better. Anyway, and here it will show you the radiation pattern of the antenna. And here in different colors it shows you the dBi gain. So this is what we want for a Yagi. There's the maximum gain out front, the minimum gain out back here as the blues. Now if you want to have a transparent display to have a look at it a little bit differently, there you go. If you want to have a look at a 2D slice, whoops, here we go, 2D slice, there you go. If you want a 2D slice, multicolor, and there you go as well. But let's just go for the multicolor one. So there you are. So I'll just make that full display, full screen, and there is your 50 megahertz 2-element Yagi in all its splendor. So you can have a lot of fun with it. It's a great program. With thanks to Ari Vors for all of his hard work and for providing it free. And I wish everybody good luck and a lot of fun when using it. So from me, 73s, and have fun.